let's talk about lines now. Here's a line. Oop, there was a line. Here's a line in R2. Ultimately, what we'd like to do is describe this object, this line, mathematically. So we need a way to write down an equation, for example. We can do that, of course, by looking at a point that it goes through, and then another point over here, because two points determine the line. Only one line can go through those 2 points. So if we isolate 2 points, that describes the line. But we can describe the relative position of these 2 points by looking at the horizontal distance between them and then the vertical distance between them. Okay, this horizontal distance is called the run, and this vertical distance is called the rise. Okay, that might look familiar. Put them together. Get the rise over the run. That's the slope of the line. Once we have that and a point that the line goes through, usually what we take is this point here, which is the y-intercept. Okay, and we write that as b. I'm not sure why we chose b, but that's the letter that's widely used to represent the y-intercept. Once we have these two, we can write an equation for the line as y equals mx plus b. Okay, but this isn't the only way we can write the equation of a line. We could also think of the line going through that point, sure, but rather than picking a second point, we could think of it as going off in a certain direction. Once we add this point, thought of as a vector, to this vector, we get another, like this, and I could imagine stretching out that vector by multiplying this vector, let's call it v, by scaling it. And if this is p, this would be p plus t times v. And I could change that parameter, and I scale out that vector, and I would have a new representation for that line. Okay, that's the one we're going to look at today. That's called the parametric form. And that's still not the only way we can describe a line. We might also pick a vector that's orthogonal to that line. Let's call it u. Then the line would be described in terms of a dot product. So if u is this orthogonal vector, I can write the line like this, being all points x and y that are orthogonal to u. And if in this case the line is shifted away from the origin, I could just write down how far it's been shifted by. Okay? So these are 3 different approaches to describing a line mathematically, and we'll take a look at these 2 on the left, which are unfamiliar, likely. So let's start with that vector equation. I'll dive into this example to explain it. Here I start with this point at 1, 1. The line's going to be going through there, and it's going to be in the vector, or in the direction of the vector 2, 1. Okay? So you can imagine adding these 2 together, and I would get this point. Okay? I could imagine having this vector, so it would be 1/2 v. And then if I add that to p, it's going to be roughly about here. Okay? That would be p plus 1/2 v. So this point over here is p plus v. This is p plus 1/2 v. This is p, which is the same as p plus 0 v. And I could keep on doing that. And eventually, all these points, they would form a line. Like this. Okay. Oops, this should have been, sorry, 1/2 v. Like that. So what I'm doing is I fix the point P, that's the point the line goes through, and then I add the vector v to that point, would give me a resulting point on the line. But now if I scale that initial vector v and then add it to P, it's going to give me another point. And you can imagine doing this again and again and again, that you keep on scaling v and adding it to P. And if you go through all possible scalar values, multiplying that by v, it's eventually going to sweep out an entire line. So let's write that down. So I'm going to write down, that's an L. L of t, L for line, is the point, plus all scalar multiples of the vector v. And we usually stipulate that this scalar t is a real number, so I write it as t is an element of the real numbers. Okay, and in this case, my p is 1, 1, and my v is 2, 1. And there we go. That sweeps out that entire line. This is known as the parametric equation for a line. Like I said, that's not the only possible way. We could also come up with a vector that's orthogonal to the line, and then, just by virtue of it being orthogonal, if I take the dot product, it's going to be all points x and y that satisfy this equation. Okay? So we could look at that here. I'm going to draw a very crude Cartesian axis. I've got an equation for a line. This is given in just the slope y-intercept form. You can see the y-intercept is 0, and we could just very crudely write out the slope. That's a rise of 3 over a run of 1. 1, 2, 3. Put it here. Okay. Like that. So we would need, in order to describe this line, in terms of a dot product, we would need to find a vector that is orthogonal to this. Okay, so we'll call that vector u, let's say. And we need to find these values u1 and u2 that are going to be orthogonal to this. Well, we could look. We know that this line also goes through this point, which is 1, 3. So this vector has to satisfy this equation. Oops, sorry, u2 equals 0. So any u1 and u2 that would satisfy this is going to work for our purposes. Okay. So I could pick, for example, I could pick -3 for u1 and 1 for u2. And that will satisfy this condition. Now to write out the line, all I have to do is just take my -3, 1, and dot it with xy, set that to 0. And this is actually an equation for the line. We could rewrite it slightly, doing that dot product, and we would have y minus 3x equals 0. Okay? And not surprisingly, if we look at this, simplified it further, moved the 3x over to the other side, we arrive back at the slope y-intercept form. Okay, so the point here is that you can conceive of lines in different ways, okay? You have that slope y-intercept form at your disposal. But you could also think in terms of vectors. You could also think in terms of the parametric equations, okay? These are different perspectives on the same thing. Now, the strength of that is that we can think about higher dimensional linear objects if we have these multiple perspectives. In particular, planes. So now, a plane we're all familiar with. We think of the plane as two-dimensional space, kind of like this sheet of paper. We can think of it in terms of higher dimensions, exactly as I have in my hand, right? This is a two-dimensional plane, a segment of it. Planes go off to infinity. But I'm holding it up. I live in 3 dimensions, so this plane exists right now in 3 dimensions, okay? And similar to a line being determined by 2 points, a plane is determined by 3 points. Okay? You can try it out at home. The plane is completely determined by those 3 points. These are intuitions that you have, right? You can go out and experience that. We want to write down an equation for the plane, though. And perhaps the easiest way to do it is to adopt the perspective we just saw for lines. You have a plane hanging out in 3 dimensions. You could imagine there's a vector residing on that plane that's orthogonal to it. Okay? Just like we found an orthogonal vector to the line, here you might imagine an orthogonal vector to the plane. This vector is special. It's called a normal vector. And it helps us out quite a bit, because if we want to find the equation of a plane with normal 1, 2, -1, well, that plane, if this is the normal, that plane is just all points, consists of all points that are orthogonal to this vector. Okay. I'm going to narrow this down, though. I'm going to say it goes through the origin, because we're going to deal with a separate case in a moment. Okay. So I know, in particular, if I sub in 0, 0, 0, the origin, I should get 0 back. But let's do it. This plane is described by all x, y, and z, so that when I dot that point with the normal, I'll get 0 back. So if my normal is just 1, 2, -1, if I dot that with any of these x, y, z, I'll get 0. That simplifies a bit. I can just carry through that dot product. I would have x plus 2y minus z equals 0. And that's it. That's the equation of the plane that we're looking for. Pretty simple. And actually, totally analogous to the line case. Okay, but as we saw, we've had examples of lines not going through the origin, but being shifted up. You can imagine it being shifted slightly like this, and going through a new point. Okay? So in the last example I did, the plane was going through the origin, but it doesn't need to. It could be shifted up away from the origin. Okay? If that happens, all we need to do to describe it in terms of a dot product is look at how much it's been shifted. So if this is a new point that it goes through that I'll call x1, y1, then I could just do this here. And what this is saying is really these negatives. You can imagine I'm subbing in the values of this point, x1 and y1. If I subbed it in, I'd get 0. So it's like by subtracting these, I'm shifting the line back to the origin. That's kind of what it's like, Okay, so what's happening is I'm using the previous case, my previous understanding, to generate a new solution for this new scenario. Okay. Same thing applies for planes. So now I have a plane that doesn't go through the origin, is shifted off of the origin, has this normal here. So if it did go through the origin, all I would have to do is just go n dotted with x, y, z, and set this to 0. That's if it goes through the origin, because if I plug in 0, 0, 0, that's going to satisfy this equation. But I don't have that case here. It goes through this point. So now I take my normal and I dot it with this point, like that, set that to 0. Oh, sorry. I went on automatic mode and made a writing mistake. I'll do it again. No way am I going to stop the video and start again. I've got momentum. I need to take x minus the point, y minus the y value of the point, and z minus the z value of the point. And in this case, if you plug in that point here, if I plug in 2, 1, and negative 3, I would get 0, 0, 0, which satisfies the equation. So this completely describes the plane that goes through that point with this normal. Okay, and I could simplify it a bit by doing this dot product. I'd have negative x plus y plus 2z and this would be 2 minus 1, so 1, plus 6, so plus 7, equals 0. Okay. Another way to describe planes. So, that's it for now. I'll leave you with some problems to do, and then we can talk about this next time we meet.